Okay, hello, good evening, everybody. Can you hear me? Can people hear me? Can you give some reaction, please? Uh, okay, thank you. So, I was actually waiting for some more people to join, but I think attendance may not be very high today. So, I think I'll just start. So, first thing is the schedule for the electronics lab. It will be a little bit hectic in the coming few days. So this is the discussion for experiment 3, which is actually the second experiment of the digital part of the lab. And the deadline for experiment 3 will be August 7th. So August 7th is the Friday. Friday, August 7th is the deadline for the submission of the week 3 experiment. And 7th of August is also the deadline for the week 4 experiment. So both week 3 and week 4 will have a combined deadline for 7th August. And for the week 4 discussion, we would like to have a session on Monday, 3rd of August, Monday, same time, 7 to 8 p.m. Same time that we had our doubt clearing session in this week. We hope to hold a full session for discussing the second experiment of the analog part, which will be week 4. So Monday 3rd we will have that discussion hopefully, and on 7th you will have your deadline for the week 4 and 3 together. The good news is that week 3 and 4 are two of the shortest experiments in this lab. So this pace up schedule that has been provided to us, it's a good thing that it is coinciding with week 3 and 4, because these are actually two that can be wrapped up in a small amount of time. Week 3 in particular is an extremely important experiment for the digital part of the lab, but it's also a short one. And today we would like to see everything that happens in the discussion in the week 3 experiment. So some people have been worrying about week 3 for a while, but I think we had already made clear long time ago that week 3 deadline is separated from week 1 and 2. So I hope nobody is concerned about that anymore. So without further ado, let us start with the discussion for week 3. I'll just motivate why we are doing this experiment. So for that, I will start sharing my screen. So hopefully my screen is now visible. Is my screen visible, people? Some reaction for that, please. Is my screen visible, or do I need to? Can you
No,
see my cursor moving? No.
yes, cursor is moving. I mean, nothing is appearing still on the.
That's because I have not put up anything. Now you may be able to see this writing pad. Okay.
Yes,
This is
that
okay
is.
now. Thank you. So let us start discussing what we have to do in experiment 3. So experiment 3 basically is the most standard thing that happens when you have any digital circuit with you. You have a 4-bit input sequence to your digital circuit. Let us assume you have some digital circuit. I'll just make something. It can be whatever. It needs to be provided a 4-bit input. So when you have 4 bits on the input side, what number of possible combinations can be there? So that is 2 to the power 4 possible combinations. You can have 2 to the power 4 possible input combinations. And you need to provide all of these 2 to the power 4 input combinations you need to provide to your digital circuit. And maybe it's generating one output, maybe it's generating two outputs, 3 outputs. Doesn't matter how many outputs it's generating. Basically, it will take all 2 to the power 4 of these input combinations, and let us say it is generating one output only. So one y it is producing, and we will see if we are getting the correct y for the appropriate input combination. So we have a truth table. When we have digital circuits, we have something called a truth table. And what that does is it maps input combinations get mapped to outputs. So in order to see that our digital circuit is properly producing the desired output from the desired input combination, we need to provide all of these inputs to it. And that is where our counter comes in. A counter is a device that is capable of generating these 2 to the power 4 input combinations. Why 2 to the power 4 only? Because it is a 4-bit counter. So it will count from 0, 0, 0, 0. It will step up to 0, 0, 0, 1. And in increments of 1, it will go all the way to 1, 1, 1, 1. So this is the binary representation for the number 0. This is the binary representation for the number 1. And this finally is the binary representation for the number 15. So this is a counter that goes from 0 to 15. And in the process, it ends up generating for us the 2 to the power 4 combinations. Right? Actually, different direction this coming. It comes in here. So these are 2 to the power 4 combinations of 4 inputs that can be fed as input to some digital circuit. That requires these inputs to produce some output. So this is the basic testing device. If you can generate all the 2 to the power 4 input combinations for some 4 input digital circuit, you have basically tested all the possibilities that a circuit is designed to operate on. And that way you can verify your truth table. So this is some sort of testing device. The counter IC produces outputs which you can use to test your 4 input digital circuit, because it will sample all of those combinations that it can receive. So that is why we want to do this experiment, to see how we can actually make use of this IC and do this particular part. Doing this particular part is not really relevant to us right now. Right now, we will just want to focus on generating all these combinations. So the IC that we have chosen for this purpose is called the 74LS163. This one. It's a 4-bit binary counter, right? And what we need to see here, one of the stated objectives of experiment 3 is to read and understand the data sheet. So using this data sheet, we need to be able to see how we can control this counter IC to do what we wanted to do. So previously in data sheet discussion, we saw some discussion of the electrical characteristics. We saw what is meant by maximum ratings, what are the operating conditions, what is meant by all these values that are listed here, what they really mean, and some current limits we discussed, what kind of current you can input and what kind of current you can draw out of the output. All of those things we discussed last time. So hopefully that will be helpful for you when referring to the data sheet of this new IC. Now you can see that this is a common data sheet for 2 ICs. So that's why they have given 2 columns over here. This is for its 161A variant, and this also has a data sheet for the 5.4 variant, the 7.4 variant. This is for 161A. And then when you come down here, you find our relevant IC, which is the 74163A. There's also a 5.4 variant of this, but we want to focus on the columns where our particular IC has been discussed in this data sheet. So they have given some more detailed diagrams. Not really enough time to go over all of that. And there are these important things called timing diagrams. Timing diagrams, I hope you will see in more detail in the final weeks of the digital systems course and in following courses. So here is a rough representation of how this is going to work. This diagram is kind of relevant for us. What you need to know is that this is a synchronous counter. So synchronous meaning it responds to a clock edge, a rising clock edge. Right, here is the clock they have demonstrated. You see this clock for the 163A. So when the clock rises, right, this is going from low to high over here. So when the clock rises, this is called a rising edge, and that's where this 163A counter is sampling things. So at that point in time, it will take account of what are the control signals that are provided to it. So control signals we will see up when we scroll up. Some of the control signals you can see here: enable P, enable T, load, clear. All of these are control signals. These are the outputs QA to QD, which will be relevant for us when we are looking for the count. Actually, these are the outputs which will go from 0 to 15. And what more is there? Just the schematic diagram. Okay, let's go to the top, see what is there in this description. These are synchronous because the control signals provided to this IC respond at the rise, are sampled, and basically the IC responds to the control signals at the clock edge, at the rising clock edge. And then presettable, so we can see how to control them using the control signals. It will be given here. We have fully programmable. We want to see how to program them. Let me just zoom in a little so it is easier for people to see. Right, so here they have finally reached the clear function for the is synchronous, right? What we expect. A low level at the clear input. Now they're talking properly about the control signal. So clear is a control signal, and a low level, when you give a low logic low to the clear input, it sets all the 4 flip-flop outputs low. So your count outputs will all be 0, 0, 0, 0 in all the 4 QA to QD bits. It will be low when a low level is provided at the clear input. And when this will happen, it will happen after the next clock pulse, right? So that's why we call it a synchronous. So the clear is like a reset. The clear input is like a reset, and when it goes low at the next clock edge, all of the output count will be 0, regardless of the other inputs that may be given. So what other control inputs are there? Right, so they are talking about the clear only. Count enable inputs. What other control inputs are there? There is count enable input P and T must be set to logic high in order to enable the count. So if these two are not set to logic high, then the counting will not proceed. Ripple carry output we'll not worry too much about. It's when you cascade these ICs and create a 8-bit counter out of a 4-bit counter. It's possible to do that. We set stages of these ICs. One of the diagrams in the data sheet will refer to how that can be done. And from the 4-bit basic unit, you can create a counter for 8-bit and 12-bit and 16-bit and all those things. So basically, any number of input combinations for the following digital circuit can be produced by counting from 0 to some very high number of bits that you can generate by cascading these ICs. We'll not worry about that. We'll stay with our single stage 4-bit counter. Okay. Um, Fully independent clock circuit, changes made to control inputs that will until clocking occurs. Okay, so once again the synchronous part of the counter shows up over here. If you make any changes to the control inputs, enable P, T or load, there's also a load somewhere, we'll look at that as well. So they will have no effect until clocking occurs. So until the rising edge of the clock arrives, the changes you make to the input signals will not be sampled or will not be registered by your counter IC. This is what is meant by synchronous. Right, and they are talking about stable setup and hold times, which will also be discussed in the final weeks of the digital systems course. So this counter IC is a sequential circuit, and sequential circuit require these control signals because they work with some sort of step, and that step is basically the clock signal. So per clock cycle, they have a certain state, and that state is held until the next clock cycle, and it changes only at the clock cycle. That is the behavior of a sequential circuit, and this counter IC is definitely a sequential circuit. So the load input we failed to see last time. Let us see. Low level at the load input disables the counter and causes the outputs to agree with the setup data after the next clock pulse. So when your load input is high, counting proceeds normally. But when there is a low level at the load input, and that is the time when you can load a value into the counter. What is meant by loading a value? You have some input pins to the counter IC as well. So A, B, C, D represent data inputs. So if you set some logical values at these four input pins, basically you can set some four zeros over here, which will not really change anything. So you can set it if you like. It's a good idea to preset these data inputs to some known value. 0000 is a standard thing to do because those are the bare minimum that the counter starts off from. But you may not want to start from 4 zeros sometime. You may want to start from 4, for example. You want your counter to go from only 4 to 9, for example. So you are curtailing the count in some sense. You are sampling a smaller space of the 16 combinations. So you set your 4 over here. You set 0, 1, 0, 0. Like this you can set. So that is just binary 4. Or maybe I said it the wrong way. This is the MSB, I think. D is the MSB. So I should be counting from that side onwards. Let me just check. Below it must be given. Data inputs are there, but where have they mentioned LSB, MSB? Let me just see. Okay, LSB, MSB, why I cannot find? Can somebody see mention of LSB and MSB over here? Okay, I'll find for you where LSB and MSB discussion is there. Maybe not immediately. But, more likely that the D is the MSB over here. It's likely that D is MSB. Okay, I won't make any assumption on this. I'll find for you and post in the space. Cannot find it immediately. Anyway, so these data inputs are there. You can set some value over here. And when your load goes low, at that time, these data inputs get loaded into the outputs. So when your count begins, it won't begin from 0 after that. It will begin from whatever you have loaded in. For that, load needs to go high again, otherwise the count won't start at all. You will stay in a load state all the time. So you set the load pin low, you load some value into the counter, and then once load goes high after the next clock cycle, it starts counting from above that. It goes from 4, you loaded 4, so it will go from 5, it will go 5, 6, 7, 8, and then you want to stop the count at 9. So for that, you need to put some additional logic in place. immediately you won't be able to see what to do here, but it would involve setting this clear pin to a low. So this clear pin actually stops the count and sends you back to 0. So if your clear is sending you to 0, and simultaneously at that time the load is asking you to load from here, then you can come back from 9 to 4. And how we can do that, let me just show some example. So this is 9 1001, this is MSB, this is LSB. So I can take these two and send them into a NAND gate. I can take wires from these two, send it into a NAND gate like this. And I know that when both the inputs to a NAND 2 gate go high, that is when the output of this NAND gate goes to a logic low, because both are high. So 9 is the first number where both of these end up being high. There are numbers after 9 where also they go high. You will see this in 11 as well, and the odd numbers afterwards. But 9 is the first one where they both go high. So if you want to stop your count at 9, you can feed these two pins into a NAND gate. This will produce a 0, and this 0, this logic low, you can route back into your clear and load control inputs of the counter IC. So that way, clear will send you to 4 zeros. Putting load low will allow you to load the value that you have provided in your 4 inputs um, into the counter, and then when in the next clock cycle there is nothing forcing this NAND 2 to stay as 0, because these values will change in the next clock cycle. It will go to whatever has been loaded into the IC. So these outputs will become, in the next clock cycle, they will go to 0 1 0 0. So there is no longer any need for this one to stay as low. It will go to a logic high. Subsequently these will also go to logic high, and the counting will begin again. From the next clock cycle onwards, you will see 5 6 7 8, and the minute you arrive at 9, again this condition will be satisfied, that both the inputs will go high, you will get a low, and it will in this way curtail your count between 4 to 9. Curtailed count you can get. So in this way you can program this IC by by the way, this part is called a this part that is delivering the control signal is called a combinational circuit, because it is providing an output based on whatever is the current input, and it is doing it immediately. And using a combinational circuit, you can prepare control signals for a sequential circuit. Your counter is actually a sequential circuit. It changes not immediately based on the inputs that you're giving, but based on what inputs are available at the rising clock edge. And it will hold the state of its outputs, held for entire clock cycle. It will not change no matter what the change happens at the control inputs in the middle of the clock cycle, held for entire clock cycle. The output state will be held for you for the entire cycle. So that is one thing. And let us come back to this one. What we have to do in our experiment, uh, let me just go and find the experiment document. Just a second, please. Okay, I had it in the wrong folder. That's why I couldn't find it when I was looking for it. Okay, sorry for that. Here we are with the experiment of the week 3 experiment. So we have to read the data sheet. We have to understand the pin configuration. What we mean by pin configuration? What are the appropriate control signals to give to our IC? We saw all of the control signals. There are two enables. There is a load. There is a clear. And obviously we need to provide the power supply. So VCC is there and ground is there. These two have to be there for the IC to work. This will go to 5 volt. This will go to ground. And there is the most important clock signal that will need a separate discussion of its own. So it can achieve a certain functionality. We just saw its normal function is to go from 4 zeros to 4 ones, but we can make it function in a different way by setting up some combinational circuit to deliver appropriate control signals at the right time if we need to modify our counting parameters. So we want this counter to count up from, this is very easy to do. It is just the normal functioning. You set up the counter, this is what it will do. And then you have to configure the counter to count down from 4 ones to 4 zeros. So how can you make it count down? That is something left to the imagination. Okay, that's something left for your imagination. How can you come up with some combinational circuit that will provide enough control signals that will allow you to do the reverse counting, or rather the easier way of doing this would be to reverse all of these, right? So you may be thinking of inverting these numbers and then maybe you can see it going down, but how you choose to do it, that I will leave to you. Mostly the IC itself is designed to count only up, so you need to take the output and do something with it in order to see your down counting function. Right, so this we saw first thing, how you can check the functionality of a 4 input logic circuit. So you can generate all possible combinations, and that's how you can check this part. So this is the most important thing. This will need its own discussion, and this was actually a point of concern long time ago. So for this, a second IC comes into the picture. I saw somebody had posted in the group that their counter IC was not functioning properly, and the secret for that can be found in this special IC. I hope you all have this. This is the this is a special inverter type of IC. It's called a Schmidt trigger. It's a type of operational amplifier. There is a more discussion on operational amplifiers in a future diploma level course called Analog Electronic Systems. It's dedicated to operational amplifiers. And why this had to be used, let us see that over here. So normally when we are giving this clock input to our, this is our clock. It's a square wave signal. It goes from low to high to low to high to low to high periodically. One cycle of the clock means it has both the high part and the low part. This is one clock cycle. You can see one clock cycle has two edges, one rising edge and one falling edge. And this has to be given into the CLK input, control input of the 163. So if we go to the data sheet of this 163 IC, there is certain amount of current that gets sunk into the input pins. So input pins we need to see where the current rating is given. (161), where is the same for 163? Right, here it is. So you can see here for clock, this is clock, and some current is going into it. See, it's taking in some current, and if you are not able to deliver the current to this particular pin, then your clocking will not be properly registered into the IC. So when you give your clock, when you give your square wave through the ADLM kit, when you generate your clock from any channel A or channel B using your ADLM kit, you are actually not able to deliver enough current through the square wave, not enough current into the clock input pin of the 163 IC. And that is why you need to put something um, in between right here. You need to put something in between the square wave signal coming out of the channel A or channel B, whichever you choose, and the clock input of the 163. This something is our the Schmidt trigger. It's actually an inverting IC, so it will invert the clock signal you give it. It doesn't really make any difference because what will happen is that your rising edge will just be delayed by half a clock cycle. See, this is the inversion of what is given here. So this is how this will go. Rising edge will come just half a cycle later. It came over here, it will just come here. It's similar to like having sine and cos, which are delayed versions of each other. So it doesn't really change anything in particular by inverting the clock signal. The rising edges still arrive at the same clock period. This remains unchanged. The time period remains unchanged. But what we get by putting this in between is that we are able to deliver more current into the clock input pin. You can see here in the data sheet of this particular IC how it is able to hold its voltage when delivering current. So if you set it up with a supply of 5 volt, here VDD refers to the high voltage that you need to set up for this IC. Here is the pin diagram of this. VDD should be supplied to 5 volts. VSS goes to ground, and these are the other pins. This A is an input pin. This A bar is a output pin. So it will produce the inverted output. So if you give your clock from the ADLM channel into the A pin, you will get the inverted clock out of the A bar, which you can then supply to the clock input of the 163. Similarly, you have B and B bar, C and C bar, and basically there are 4 inverting input outputs available in this particular IC. This goes to ground, this goes to 5 volts. And what happens when you are delivering current from this IC, you can see here. So when your VDD is at 5 volts, you can deliver. Okay, no, this is something else. Let me come to the actual output. Where is the output? Right, IOH. How much current you can deliver when you are holding a high voltage at the output pin. I hope I am still online. Okay, fine. So we have when the output pin goes to a high voltage, how much current can we deliver? For a VDD of 5, the output voltage will be maintained at 4.6 volt even when you're delivering typically 1 milliampere. So which is much higher than what you get to see, in these ICs, where the output current delivery is actually not very good. We saw last time that it is 400 microamperes. These are called transistor to transistor level TTL devices, and right, high level output current. it's maximizing at 400 microamperes. So 0.4 milliamperes is what you can deliver from here. When you see compared to this one, it is able to deliver an entire milliampere without letting the voltage drop too much. This is 4.6 is being maintained, is very good. And even if you draw up to 3.2 milliamperes from the output, it will still manage to maintain its voltage at 2.5 volt, which you may note is higher than the VIH, the typical VIH values, which is 2 volt for this 163 AC. So even when delivering so much current out of its output pin, it is still able to hold a high level output voltage, which is greater than the VIH of this IC, which is going to be receiving that clock in its input. So this is the advantage of putting this Schmidt-Trigger operational amplifier uh, inverting gate. You can make your clock signal more powerful to be recognized properly by your counter IC. So in short, when you finally set up your experiment, your clock comes from here, from the ADLM channel. Your clock comes from here. It goes into, let us say, A of the CD 40106. You get the inverted A bar, so clock inverted, right? And you feed this into the clock input of 163. And that is how you can make it work, and it will deliver all the counts for you. So how to know that your IC is counting all the way from, how to know that your 163 is actually counting all the way from 0, 0, 0, 0 all the way to 1, 1, 1, 1. So for this, you can place your oscilloscope channel B, the other one which is not supplying the clock, channel B of the ADLM. You can use in the oscilloscope mode. So the Z or voltage measurement mode, which we saw last time. You can take it and put it one by one. If you put channel B into the LSB, this is the LSB. If you put it here, then you will see that this LSB changes at every clock cycle. So if the clock is going like this, or rather I should say clock bar, which is the actual clock for us. If the clock is going like this, then our LSB will change. It will stay 1 for 1 clock cycle, and then it will go to 0 again. Because the characteristic of the LSB is that it is the 2 to the power 0th bit, and for every addition of 1, it changes. Right? It goes 0. If you add 1, it becomes 1. Then you come to 0 again, because 2 is 1, 0. So the LSB is 0. 3 is 1, 1. So the LSB is 1. 4 again, the LSB goes to 0. It changes at every clock cycle. So you can see it changing if you probe it with your oscilloscope. Every clock cycle it changes. What happens when you come to the LSB plus 1 bit? This will changes every 2 clock cycles. Right? We can see easily. We go from 0, 0. We go to 0, 1. This bit hasn't changed. 2 clock cycles it hasn't changed. Then we come to 1, 0. This is 2, and then 1, 1. And then it has changed to 1 for the next 2 clock cycles, and it stays there until you reach 4, where again this bit goes to 0. So this one changes every 2 clock cycles. You have LSB plus 2 changes every 4 clock cycles. Right? And finally, you have the MSB for the 4-bit counter, which changes on 8 clock cycles. So the MSB is the easiest one to track. It will stay as a flat line. It will just stay as a flat line. And then it will rise up and stay as a flat line. 8 cycles. It stays as a flat line at logic low. So this is 0. For the following 8 cycles, it stays as logic high, which is 5 volt in our case, because that is our high voltage that we are using. So this is the MSB. This is the state of the MSB. This is the state of the LSB, and the other similarly. So you can put your oscilloscope probe in there and you can see the waveform. And that is how you can verify that your counter is working. The optional thing is that somebody can set up an LED circuit, but I don't want to mandate that. So basically what you do is set up the output pins QA, QB, QC, QD, and you connect them to LEDs, right? This is an LED bad drawing. So let me do like this. Yeah, that's an LED. And definitely put up a series resistor over here. Well, we have not talked diodes in this lab course yet, so I won't really emphasize this or anything. If somebody has worked with LEDs before, then they are free to try this, but this is not really needed, entirely optional. To show your outputs, you can just plot the waveform that you are measuring from your oscilloscope. Plotting waveforms we have seen last time. Okay, this LED showing the output with the means of LED. So your LED lights up, LED starts glowing whenever there is a logic high because it's getting some current. But you need to be careful of the current limit of these output pins. You can only supply 400 microamperes, and the series resistor needs to be reasonably sized for that because it's a current limiting resistor. And all that you need to do, which we don't want to get into right now. So this part is not really needed. What you need to show are the waveforms for each of these output pins. So how you can plot it? You can show a clock, how the clock is changing. And then on the same graph, you can show the, I think this is the LSB. I'll confirm it for you in the G space. You can put the LSB here. And then you can make separate graphs for them or club it all into one graph. That is also up to you. Separate graphs are nice to look at, so you can compare directly against the clock. So you can put you can put the LSB plus 1. Compare each of them with the clock, basically. Compare each output pin with clock. To show that your actually LSB is changing every clock cycle, every cycle, every this one will change every 2 cycles. So graphs against the clock. All output pins plotted against so 4 plots you can make separately for all of these 4 and show that your output is actually what you expect it to be, and you are getting entire 16 counts out of your counter when you go from 0 to 1 1 1 1. How you will get the reverse counting output, that I leave to you. It is possible to do. You stage your counting output to go through some inversion and then some combinational logic. Just inverting it entirely may or may not help you out. You need to check that. You need to write up the truth table for that and see whether simply making inversions of all these. Since you are seeing the inverter here, you are seeing an inverter IC here. So the first thing that comes to mind is that if I invert all my outputs, then I have a lot of free inverter pins, right? I have I'm using one for the clock, all the other 5 are empty. So maybe if I do that, I'll get the inverted counting, but that may or may not be true. So please write the truth table for that and see if you need any additional combinational logic and set it up. You have NAND gate, a quad NAND IC to help you with making any combinational logic. A NAND gate is a universal gate. It can produce all sorts of functions if you use it properly. And then uh, once you are done with staging your uh, um, staging all your gates and your logic such that the 4 output pins are actually going from 4 ones to 4 zeros, then you can record the output over there with the channel B oscilloscope, compare it with the clock signal and show that you have actually managed to achieve inverted counting um, from your 163 counter IC. So that is how you can complete experiment 3. And same regulations as before. Try and keep your video within 5 minutes. It would be nice if you kept it within 5 minutes. 8 limits is the upper limit, so definitely finish by then. You have to show plots for upcounting, 4 plots for the upcounting, 4 plots for the downcounting, and basically managing your counter is the um, goal of this experiment. And the discovery that you have to do it, you deliver a clock signal via the Schmidt trigger was in the original electronics lab a mystery of its own, and proved to be a very fruitful experience for all involved over there. We are just using the result from there, but that was a story of its own. So you have to supply the clock through the Schmidt trigger inverting IC. Okay, so now are there any questions for this experiment, please?
So for each LSB and this thing, we have to have connect to channel B, take the reading, and then move to the other bit, right?
Right, you have 4 output pins, so you need to put your channel B one by one.
One by one.
You have to record one by one. One suggestion I'll give you for that. Let me just go back to sharing my screen. You want to know how to basically how to plot the channel B recordings against the clock, right?
Yeah.
Okay, let me just share a suggestion with you. So let me share my screen, come here. Last time we saw in the ADLM that there is something called repeated sweeps. We actually need to discuss this. Thank you for asking that question. Reminded me of this. There is an option called repeated sweeps. When you are running your circuit, when you are running your counter IC and you want it to cover all the counts, that time you need to turn this option off so that it will continuously supply the clock for all the time that your circuit is running. At that time, you can even set your clock frequency to some lower values. You can even set f is equal to 1 hertz or f is equal to zero 0.5 hertz to see the slowly changing clock, and the slow changes will be represented in the output pins of the counter IC. So this you have to turn off when you are running your circuit to see all your counts in real time. Turn off for real time operation. Right? When you're using, this is 1 second, one cycle takes 1 second. This one cycle takes 2 seconds. So this is sort of human measurable time. But when you are trying to record the output, then that time you keep the repeated sweeps on. You keep repeated sweeps turned on, and you set your 100 millisecond recording window. So the clock will be delivered only for 100 milliseconds, and then there will be a period of silence. So the clock will be going like this. For 100 milliseconds, it will be going, and then there will be a period of silence. So this is the part where the ADLM kit is not doing anything. It's not producing any signal. and then again it gets triggered, and for 100 milliseconds it will deliver your clock signal again, and repeatedly it will do this 100 millisecond cycle of clock delivery. That is why it's called repeated sweeps. And what you can do is you need to see how to fit in 16 cycles, 16 clock cycles within the let us say 100 millisecond. There are also more um, time windows for time windows for which you can measure your signal. There is 1 second, there is 10 seconds, there is 10 milliseconds. This one I find most comfortable. You can use these also. You can use the others if you like. This one may not be very helpful, but you can use 1 second. That increases the size of the data you get, lot more data points in there. So I find this one actually comfortable. Anyway, so you need to fit 16 cycles within your sweep window, right? So if you want to fit 16 cycles within your 100 millisecond window, sweep window, this is the sweep window. What you need to do, if you do this, what you get some I think 6.25 millisecond. That is your time period of the clock. So what does this time period mean in terms of frequency? Frequency of the clock will be, why am I writing TS? I can write TC and make it look much better. Okay, so what will be the frequency? It will be, right, and this will be, how much will this be? 1000 by 6.25. So 6.25 for 16, 10. Okay, so I think this will come out to be 160 hertz. So if you set your frequency to be 160 hertz, you will get exactly 16 cycles within the 100 millisecond window, and you can use your channel B as your oscilloscope during that time period. So channel A, you will see 16 cycles of clock being delivered. In the channel B below, you will see 16 cycles of output being recorded. For the LSB, it will be changing per output cycle, per clock cycle. For the MSB, it will change only once after 8 clock cycles and will stay that way. And in this way, you can produce the data, you can export the data, you can save the data and plot it out in Excel, or you can directly show the pixel pulse. You can directly, if you are able to screen record, you can directly show with the help of your pixel pulse itself the waveform output that you see on your pixel pulse screen. If you are able to screen record, you can show over there. But the problem there is that they don't show the vertical bars in your clock, in your square waves. So you only see the top rail and the bottom rail. There is no vertical line in between. So when that goes missing, it becomes a little difficult to see on the pixel pulse screen. You can manage that by changing your dot brightness, but it is cleaner to actually plot it out on some plotting software, so that the vertical lines that we associate with the square wave signals, it's what our mind is used to. We are able to easily see that when we do that. Okay, so does that answer what you were asking, Netaji?
Yes, sir.
You have to do that for each of the output pins. There are 4 output pins in your IC, so you need to do that for each of those and plot it against the clock signal for each of them, so you can directly compare over there. 4 plots, 1 plot per output pin, clock versus output pin, like that. Clock versus QA, clock versus QB, clock versus QC, clock versus QD. The LSB and MSB I'll put in the G space. I don't know how I forgot about that. Is that okay?
Sir, I want to ask something.
Please go ahead.
Like for this online lab, what is the criteria? Like there are 8 labs. So
There are
from
8
those
labs.
8, how much we have to complete to qualify?
Please submit at least 5 proper assignments. At least 5. Properly.
Okay.
Do
Okay, I want
nicely,
to ask something.
properly, at least 5.
As I submitted the first one,
Hmm.
in first one, actually my multimeter, the multimeter I have, the multimeter, it is like not working, like it is damaged. So I have told in that video. So is it okay?
Uh, the person who is evaluating the video will be able to take a better judgment on what exactly the situation is. Multimeter we need in there for being an outside referee for the for the signal that is being produced. You can measure the voltages using your oscilloscope channels provided on the ADLN and report that voltage is this and voltage is that. That is possible to do. Multimeter was recommended there for being an external referee. It
Yes.
becomes easier to see the DC signal through there. So that's why it was there. Anyway, if you have shown using your channel A and channel B, you have managed to do that. So there may be a workaround for that, but please get a working multimeter. That would be my
Okay,
suggestion.
sir. Okay, sir. And what is the deadline of week 3?
Week 3 is August 7th, along with week 4. Week 4 we will hopefully discuss on the coming Monday, the 3rd. Same time, 7 to 8 p.m. Hopefully.
Okay, sir.
Any more questions, people?
Sir, one thing to inquire.
Please go ahead.
This we are getting some mails regarding slot booking for the live lab, I mean offline lab,
Correct.
in-person labs, right?
That is right.
Is there any criteria as well to attend that? I mean, is there any eligibility criteria?
Yes, you have to score enough in the online lab. You have to submit, like I said, at least 5 good and proper experiments you have to submit.
But that we will get to know when we will complete all the 8 weeks, right?
Yes, you have to keep submitting, and then you will be called up for the offline or in-campus demonstration based on the performance in the online lab.
Then what about selecting the slot now?
You have to select the slot now. They have mentioned, I think, a date over there. By 2nd of August, you have to choose some slot so that you can be allotted that point in time for attending your in-campus demonstration, and you can make travel plans accordingly, right? You have to travel to Madras, and that is also a challenge of its own. So that is why the slot booking and dates have been released for you to plan your travel and for you to indicate when you want to attend, so things can be arranged for you accordingly.
Sorry to interrupt, sir. The same topic. This booking, no, sir. The booking, the page is not opening. It seems to be access denied. It's not yet open completely, I believe.
I saw that issue, so I think they will do something for it, and it will be, you will be able to open it soon enough. I have seen that issue. I also have some labs, so I was also looking at that page. I know that.
Sure. Sure.
Okay, we just
Thank
need
you
to
very
be patient for it.
Sure. Thank you very much. I already put it in the support. Just to what do you call it? Check with you. Also, you also face something.
It's like that right now. Don't worry, it will be rectified in time.
One thing more, I am planning to do this in-person lab in the next term, not in this term. I want to club it with other labs.
Correct.
So, will I have to do this assignment submission now, which I am doing now online, and again I have to do it for next term, or once I do the online labs and do the in-person lab in the next term, is it possible?
So personally, I have never tried splitting it up in this way, in this particular way. But what I understand is this: if you gain your eligibility to attend the in-person demonstration in this term itself, right? You submit all your assignments, you submit your 8 assignments, you score well in them.
Yes.
You have gained your eligibility to attend the in-person demonstration. Now you can use this eligibility in the next term. So it's like it's not possible to separate all your assignments across 2 terms. Like you submit 4 assignments in this term, and then you submit 4 more in the next term, and then thereby you gain eligibility. I think that is not possible to do. What you can do is you can gain eligibility in one term and then use it in the next term. So please get this clarified with someone in the support team. Just ask this thing. There is something called I grade. It's called incomplete grade. So what it means is you gained the eligibility for attending the in-person demonstration. You chose not to attend it at the end of this term. You chose to attend it at the next opportunity, that is one term later, because project registrations they have made, so the project registration lasts for 2 terms now. So you read the grading document and you post this to the one of the support groups. I think ES Foundation group you can ask, or in the ES student space. I think it is possible to do it like this, that you gain eligibility in this term by submitting all your assignments and attending comfortably in the next term.
So you said I grade. I grade is something adverse which will reflect in my final grade sheet or mark sheet. Is it?
It doesn't carry any weightage in terms of affecting your CGPA. It's I, it's just incomplete. It's like your progress is held over there. When you get some grade, you got an A grade or an S grade, the points get added to your mark sheet. But I grade, nothing is happening yet. Until you get the final grade for that course, your credit and grade for the credit are held in place. That is what I grade means.
So once I attend the in-person lab and complete it, the I will be replaced by something, and nobody will get to know that I was having I something. Is it?
Yeah, I will show up for the mark sheet of this term. That's not a problem. It just says
Okay.
that the course is not complete. And once you
Okay.
complete it, your final grade will show up, uh, whatever it is, the passing grade that you have got between, various passing grades, all the way from S to, I think, even D is a passing grade. So all of those are
Yes.
passing grades, and the final grade will show up once you complete your in-person demonstration at the second chance, basically after one term. But if your course registration itself collapses, somebody doesn't manage to attend the in-person lab within 2 terms of registering, then it's a separate situation, and that I think gets a U grade, which is basically a failing grade. Then you have to register afresh and stuff. I think that's how it works.
So in this case, I do not have to re-register for this coursework again.
As far as I'm aware, the
Okay.
registration for projects, labs are called projects. Okay, so that
Okay.
lasts for 2 terms. You please confirm this in the latest grading document and ask someone in the support team as well.
Actually,
Okay, please don't take my word as gospel for it. Just confirm it.
got it. That is fair enough. And okay, this was my query. And one more thing. Recently, I got this kit. I mean, through because of some delivery issues.
Right, right.
I have to start with the first one. Uh, I mean, now only. And my query is that in the demonstration, under that project work, some objective is not mentioned for experiment one specifically for week one. What is the final objective? What I got to know is that I have to draw a VI characteristic. Is that the only thing required?
So what you need to show in the video, we have discussed in the week 1 session. Okay, you go back and refer to that session, what you need to do over there. The
Yes.
voltage transfer characteristic is an important thing that you need to show somewhere into the video towards the end. You need to either show it by means of screen recording, or you need to edit the screenshot into your video. You have to show that curve. That is important. We have discussed what you need to show in the submission in the week 1 session. You can revisit that.
Okay. Fine. This is right.
For week 3, this session is for week 3. So if there are questions regarding week 3, please ask them.
No, like some of us are still stuck at week one, so this is the issue. We will go up. So once we get to know how
No,
to,
so your
how,
case is separate. But
yeah,
my friendly advice to everybody in this situation is, please focus on week 3 and 4 for now. For a minute, just forget about week 1 and 2, because week 3 and 4, the deadline is 7th August. So focus on submitting on time what is within your hands, right? You are able to submit on time what is in front of you. So focus on week 3 and 4 first. That is my friendly advice to everybody in any sort of position. If your week 1 and 2 are delayed for whatsoever reason, forget about them for the moment and focus on week 3 and 4 first, because these are immediate priority. Okay, including you. I give this suggestion for everybody, including you.
So you suggest us to do it later on, week 1 and 2, is it?
First, you worry about what is in front. These are deadlines that have to be met, right? So 2 weeks are there. You focus on this. If you get done with your week 3 and 4 by 7th, then you start wondering about week 1 and 2.
No, but for week 1 and 2, nobody will extend it too much, na? I mean, now
Week
we can get at least extension.
week 1 and 2, your situation is known to the team, right? Support team knows about your situation, instructor knows about your situation. So once you are ready with your week 1 and 2, you need to write to them to enable them to reopen the form for your submission. That's how that will work. Of course, it will be nice if you do it as soon as you can. That will help everybody all around. But for the present, my recommendation is to focus on week 3 and 4 first for everybody.
Okay, right.
Any more questions about week 3, please? It's an extremely important experiment. Even though it is so simple and not much is happening in it, the entirety of the digital part of the electronics lab is based on what you get out of week 3 experiment. So this experiment really is the most important experiment of your digital part, and where the electronics lab really begins. So even in the GSpace, if you have any questions, you can post your queries over there. Even if not me or the course instructor, some of your friends can also answer. I saw some discussion over the past couple of days where people were answering each other's queries, which is very nice to see. That is what that GSpace is for, an open forum for helping each other out when you have queries. So nice to see people making use of it. Week 3 experiment, please read the data sheet thoroughly, all the parts of the data sheet. Whatever you can understand, you try and extract out of it. That is an important goal of the experiment itself. The data sheet of the 163 IC in particular. The Schmidt trigger IC, the data sheet is not that important for you, but the counter IC, the 163 IC, the data sheet for that, you definitely read in full. So there may be different manufacturers and they may have different data sheets for their, differently worded data sheets, let me say it that way. Data sheets will have different information for the same product for different manufacturers. Try and read multiple data sheets from multiple manufacturers to see what are the various types of information you can get for the same product. I think I also had read multiple. Let me see if I can find the other one that I had. The data
Hello.
sheet itself. Yes, please go ahead.
So week 1 experience, one capacitor is there. It can be 1 nanofarad also, okay?
You can use whatever. We have discussed the capacitor issue in the week 1 session. You can refer back to that session and see what exactly the capacitor is doing, why we need it, and what type of capacitor you want to use, and how we inform our opinion on the size of the capacitor. It's there, I think, in the week 1 session. So you please refer to it, okay? Session recordings are all posted to the group, so you can see. Yes, I found something nice here. So I will share my screen again. I found the IC data sheet for a different manufacturer. I did have it. So this let me hide. I hope you can see my screen again. So you see this one. This is from Texas Instruments. And it has a lot of ICs are clubbed into one single data sheet. And here you can see the name of our particular one that we will be using. This is the one. From all of this that are clubbed into one single data sheet, here is this. And you have description. You had a description for the same IC over here. This is Fairchild Semiconductor. This is their description for their for the same IC, their product. And you have some more description, so more information. You can see something extra here as well. And let's see if we can find out which are the MSB and LSB in this IC. I think it would be given. You can read this paragraph entirely. You can get some more information for your device through this thing. What I wanted to find was the MSB, LSB information, very crucial information that somehow I missed out on. data inputs, data outputs. Okay, I can read it from here. Okay, it says QA, QB, QC, QD, and this is 9. So what is the state of these? So for 9 we have both of these up. Okay, for 1, which is the one going up? For 1 we have QA going up. Okay, so QA is high when the count is 1, and then for 2, what is happening? QA has come down and QB has gone high. So QA is the LSB. QA is definitely the LSB. At 0 it is low, at 1 it goes high, at 2 it goes low. So it is alternating with every clock cycle. On every count, QA alternates. So flipping of the bit on every count cycle is the characteristic of the LSB, and QA is definitely the LSB. So that makes QD the MSB. Okay, I'm glad I could clear this up here itself. So we can read it out with the help of this timing diagram. And for the data inputs as well, here they have shown how to load some data inputs. So you see A, B, C are high, D is low, and at that point they have set they have basically loaded the input in. So what has got loaded in is 7. So 7 being from the MSB side, 0, 1, 1, 1, same as what you had here. So D is the MSB for the input, A is the LSB, and 0, 1, 1, 1, 7 they have loaded in, and that is why the count has started from 7 here. On the next clock cycle, 7 has become incremented to 8. In the middle of 7 and 8, they made sure to send enable signals to high, which will start the counting, and the other control signal they managed to send high as well. So they set load to low, it got sampled at the rising clock edge, the low in the load signal, and that allowed the whatever was put into the input bits to get loaded into the output on the next clock edge, right? And then they set load up before the following clock edge arrived. In the middle they also sent the enable signals high, and that is how at the next clock edge the 7 turned into 8. Here you can see the MSB going to 1 and the 3 lower bits are 0, and the count has started. And then how did we come from 9 to 0? That they have not explained yet, but you can do that by doing clear or some other combinational logic using the outputs of QA to QD. This same graph is given here as well. You can read it with the help of that. I think the configuration is the same. If D is the MSB there, it must also be the MSB here. Right here they have shown like this. So in 15 all are high, and QA is alternating with every count. So it is the LSB. QD is the MSB, and these are the inputs you can use to load some value in. Same thing they have given here. Okay, I hope this part is clear. I missed out on this when doing it on the first go, so I'm glad I was able to cover it before the session ended. I hope that part is clear. Anybody has any questions? And I'm sorry, we seem to exceed our time every time. It was already 8 o'clock some time ago. But this is also a 3-credit course. So the amount of content that needs to be delivered is quite big. I'm sorry about exceeding the time, but I think what I feel is that the content deserves the discussion. Somebody wants to ask anything? Please go ahead.
Sir,
Yes, please.
sir, actually, what happened is for my kit, I already ordered. Still, the kit is yet to come. Basically, I asked Mr. Mohammed Khalil, I believe. I think still arranging the delivery. I think it's taking a little time. Should I inform the POD, Mr. Vishal, about this?
Yes, keep him in the loop.
Okay, because I was somehow I tried my level best to arrange a local one IC for the week 1 thing. So I just prepared just now. I prepared the week 1 content to upload, but still I am looking for the component. Some of the component, as you said, it is still not available in the market. We have to completely trust the component which comes from the IIT Madras. So in this case, I'm clueless when I'm going to get and complete these labs.
You have my sympathy, Mr. Shivakumar.
No problem. The thing
I,
is like,
I appreciate how understanding of the situation and how compliant you have been with this whole thing. I appreciate your approach to this whole situation. You have my sympathy, but one thing we see is that I don't want to say it in this way, but the project registration lasts for 2 terms, and I think that may come into play for your case. It may end up being that way. I don't want to say it because I hope your kit and components arrive soon enough for you to allow you to submit all your assignments within the term and attend the in-person lab. But this situation is becoming more and more difficult by the day, isn't it? Days are passing by, and the operational
unfortunately,
issues.
for the week 3, I cannot able to, because week 2 is nothing, just resistors, and week 1 also somehow I arranged the component. But the week 3 is difficult for me to get the component. Very difficult in the market.
It is difficult
because I am.
Sir, I am telling the same issue I am facing.
Any other
just one
source to get it.
Sir, this one first week
can just
only you
make my
relaxation
status
for 4 to 5 days. This is kind request. That is my point.
Devraj, just hold on.
Thank you very much.
Just hold on. Let me finish with Mr. Shivakumar first, please. So, Mr. Shivakumar, like you were saying, the first week 1 experiment you may have managed to do with a 5 volt voltage source.
Ahmad, your voice is not there.
My voice is not there. Is it better now? Let me. Is it better now? Can people hear me? Can people hear me now? Am I audible? Let me write here. Can somebody please respond?
Yes, you are audible.
Okay. Mr. Shivakumar, you were saying something. Let's finish with your issue.
I think Shivakumar is mute.
Is it?
Yeah.
Okay. So, thing being that in the digital part of the lab, the IC and the exact IC that you need become important. That is why the institute discourages people from buying on their own, because you can see here, I have shown the data sheet, and small changes in number and alphabet actually change the product by a little bit, and those things start to matter at some point. That is why you need the component set delivered properly so that you can conduct the digital part of the lab. In particular, even in the analog part, you start needing the kit. Like we saw in the week 2 experiment itself, we need to generate sine wave and high frequencies and low frequencies, and for all that you cannot do with a constant voltage source. A 5 volt battery may be enough for week 1 alone, but going further it becomes more and more difficult. So people who are facing component delivery issues, the operations issues are really the area of the support team. I am part of what is called the academic support team. So questions about the experiment, the content of the experiment, conceptual questions, those things I am able to handle. But the operational issues are really beyond my power.
Tanjil sir, we understand your point very well. But please, I am telling one thing, part that if you extend 3 to 4 days, I am telling 3 to 4 days, it will not hamper any other schedule. That is the point. Okay.
No, for you, for people who are facing issues.
No, it is not my. It is not myself. If you see the GSpace request, there is many people are requested. Okay.
I know that people are requesting, but there is a schedule we need to keep up with. There's a reason the deadlines are in place, and 3 to 4 days.
I am telling one thing. There is a many area. I can show you proof right now. Their IIT Madras are extended, delayed. Even they have delayed the registration process also, admission time. Okay.
See, all these issues you take up not with me.
I
What I can
understand,
tell
but
you,
it is
no,
what is
please
happening. Right? It is
understand.
one-sided communication. हो रहा है. It is one-sided communication. It is not a congenial type. It's not. We are learned, na? It is not
Devraj,
given.
this discussion I cannot allow in this session.
No,
I'll
no.
have
It
to
is
mute you.
not
If you
allowed.
insist,
No, I
I'll
am
have to
telling you
mute
the
you.
fact. I am telling you the fact. That's it.
This particular issue we can't have discussion on in an academic session. Yes, Vishal, please go ahead.
Sir, just a suggestion required from you regarding making a video that while showing my breadboard, I will use the mobile phone, right? Through mobile phone, I will show what is on there on my breadboard, right? And for displaying the graphs, etc., I will shift my shift it to my screen. Is it that way? I will make the video.
So if you shift it to your screen, how clearly is your screen visible on the phone camera? That is one thing. So one thing that people do is they take a screenshot of their plot and they edit it into the video as a still image. They edit that frame into the video. Or what some people do is they screen record, right? Screen recording software, and they show the recording of the screen for those few seconds and they talk over it. Or if you are able to um, manage the optics in such a way that what graph you are showing on the screen is very clearly visible even on the camera recording that you are doing, as in you're recording your table, your laptop is part of the recording frame, and we can see very clearly all the numbers, the digits, the plot graphs and legends, and everything is very nicely visible because you have manipulated the font and everything very nicely. So then that also works because we need to see the graph, and if we can see it clearly on your screen that way, then that works. That is something for you to manage. Actually, you can do it, but it will take some careful handling.
So you mean, sir, normally what people are doing is they are editing the video and creating two videos and merging it, or multiple videos then merging it. And is it that, or some?
People do some editing, some basic level of editing.
Okay,
So
okay,
what people like to do is that they don't want to do fancy editing. So they take the screenshot and they edit the still image into, you show the still image for a few seconds in the end of the video. So the graph that you wanted to show is clearly visible. So
okay.
that's how people like to do.
So can you suggest me some software of that kind so that I can also use that, or one?
Uh, it's all, Google uncle.
Okay,
Google uncle has
fine,
the
fine.
answers.
One workaround can we do? Like I will create a Google Meet, and on my, like in what in OPP we do. I will focus my mobile camera to myself or my breadboard, and then show whatever is there through my ADLM kit on the screen. Shifting the screens. Is it okay?
Very complicated workflow. At the end
No.
of the day, we don't care how you do it, as long
Okay.
as what you are showing on the screen is clearly visible.
Because in OPP normally we do same thing. I hope you also doing same.
As long as what you are showing on the screen is clearly visible and readable
Okay, okay,
in the video,
yeah,
you can manage in whichever way,
fine.
whichever workflow allows you to do it. The digits and the graph lines and the text and all that should be
Yeah,
readable.
got it. Thank you very much.
Any other questions?
Like, I have a question.
Yes, please go ahead.
So, I kind of, while doing the week 2 experiment, encountered an issue where I had to generate a millivolt wave, which is not possible in pixel ones.
A
So,
millivolt, why was that?
it was particularly, they asked us to also create a circuit with V-Thevenin or the Thevenin circuit, and also measure the corner frequency for that. So when I calculated the Thevenin, it somehow resulted in millivolt. I don't know if I did the calculation wrong or something, but would that be the case? I don't really know.
So I don't think millivolt comes into the picture. What
Okay.
happens when you do the Thevenin equivalent is that you just generate an equivalent resistance onto which you are supplying your original signal, and at the output of the resistance is what you is where you have connected the capacitor, and from there you are measuring the output voltage.
Yeah, I do get that, but I don't know. I'll just recalculate it. But and also while doing that, I just realized something that there are many other softwares for Adal than Pixel Pulse only. So is it fine if I use them too?
There's another one called Alice. I think Alice is one
Yes,
that
there's
people
Alice,
use.
and there's also like even more GitHub. Since it's open source, like there's just a there's a multimeter software for Adal, so it just does what a multimeter does, and so on and so on.
Personally, I haven't used anything other than Pixel
Okay.
Pulse because it gets everything done for me, and I like how it is
Because
designed and
currently what's happening is in Pixel Pulse, when I want to take a differential voltage, that is, it's only the channel A is always between the voltage measured and the ground. So if I want to take a differential voltage, it's not possible in Pixel Pulse.
I think I showed you that in the week 2
Yeah,
video.
yeah, that
How
was
to
also
do
there.
that. So you have to do some jugglery, but you can do it. It's possible to do.
But it was quite hard, so I just found another software that does it like just simply. So it's like,
Okay, if it works for you, then it works, right?
okay, okay. I was just asking if it's
Bumblebee kit users have it easy in that regard. So if you find a way to do it easier, then that's okay.
okay. And I don't really know what exactly this Bumblebee kit is. So is it any like a
It's just
different?
ADLM when ADLM is not available. So these are the kits that have been supplied to people when ADLM could not be sourced. It's the same thing.
Okay,
It's an analog board, same type of product with some extra features.
okay, okay. Thank you. Oh, I
Okay.
also got another doubt that suppose like the week two was completely filled with parts, right? So part one, part two, part three, and so on. So I was unable to finish the
Correct.
entire part three. Like I think I could not finish one of them. Is that fine if I submit it like that?
Best thing is to submit at least something. That I will always recommend to people.
Okay, okay. Because part three, I kind of finished it, but only one objective was not done in part three. Like there are some
Okay.
five or something.
See, compared to no submission, a somewhat done submission is always better, right?
Yeah. Okay.
That's always there.
Thank
So
you.
you do your best and you submit. Don't worry. The important thing is to, keep moving and not be
Yeah.
stuck on these things. You move on from this, you move on to week 3, week 4, keep moving. Don't be stuck on one thing. That is important.
Yeah.
Uh,
Thank you.
excuse me, sir. Excuse me,
Please
sir.
go ahead.
One query from
Go ahead, please go ahead.
this discussion only. Is there any grading on the basis of our these submissions, or the grading will be on the basis of in-person lab only?
So there are components, you can see in the grading document what is the weightage
Okay.
for the online lab and what is the weightage for the in-person lab. That is given in the grading document. Your 8 assignments are compressed to be 40% and your in-person lab becomes 60%. I think that is the grading they are using. You please check in the grading document for more clarity.
Okay. So each of our submission of 8 out of the 8 submissions will be having some grading will be given, and out of that 40 weightage will be there, right?
Right. It will sum up to 40 in the end.
Yes, yes, right.
I think so. Okay. If nothing has changed from what I remember, then it should be like that. Please check grading document.
Okay, fine.
Okay. Hopefully that is everything. Okay. Hope to see you all on Monday, where we can hopefully have the discussion on the second experiment of the analog um, part of the lab. And we hope to discuss week 4 on there, Monday, same time, 7 to 8, hopefully. And thank you for joining today. And good evening, everybody.
Thank you, sir.